Hello and welcome to today's episode of Rawkode Live. I am your host, Rawkode, and today we are going to be taking a look at a CNCF project, CoreDNS. Before we move on to that, I just want to take a moment to say thank you to my employer. They provide me the time to invest and help produce these episodes that we can take a look at the modern cloud native landscape and produce learning materials for us all to learn together. So thank you, Equinix Metal. There is a code, Rawkode Live. You can use that when signing up, or even if you're already a customer, you can still use this coupon. It will get you $50 in credits, which you can use in a couple of hours with some beefy machines or spread out over a longer term with some smaller machines. Either way, the choice is yours. If you want to have a conversation afterwards, there is a Discord server. You can come and join and ask questions or just ask for new show suggestions. I am open to anything. And if you're not watching live, this is the best way to interact. Now we're going to take a look at CoreDNS, and for that I have the founder, Meek Heben. How are you, Meek?
Hello, I'm fine, thanks. Thanks for having me.
No, this is awesome. I'm really looking forward to learning more about CoreDNS, and who better to do it than you. So this is going to be fantastic. Do you want to just take a moment to introduce yourself and tell us a little bit about you and the project?
Yeah, Meek Heben, worked in London for a couple of years, moved back recently to the Netherlands, where I live now. And I have been doing DNS for a long time, involved in DNSSEC in 2000s. And at some point, I got involved in SkyDNS, which was the thing that got used in Kubernetes. And via some ideas, this led to me actually writing a new DNS server, which is CoreDNS, which we're going to talk about tonight. Okay,
great. So let me start with a couple of questions that I kind of prepared in advance then. So when I think of DNS, I've been doing operational work for nearly 20 years now, and bind was just always that one thing that I had installed on my server. Why did we need to change the status quo there? Why did we have to bring in something new?
Note that there's bind, there's NSD, there's PowerDNS, there's a couple of DNS servers and recursors. Mostly you don't need a new DNS server off the bat. The interesting thing here is that I wanted a new DNS server and I was capable enough to actually writing one. And it's one of the few that's not written in a C language. So off the bat, there are a couple of things that are better. It just crashes. There are no buffer overflow and that kind of stuff. So that's a big difference from the current crop of DNS servers. Being written in Go, you have GC, so there might be more overhead, so speed might be an issue. But yeah, in general, I would recommend against writing a DNS server. But to just break the mold and have something new in the ecosystem, I think CoreDNS is a very good idea. Also, if you look at DNS, the protocol is fairly complex nowadays. And I don't know from the top of my head any new DNS servers that have grown like CoreDNS did in the past year. Like its bind is from the 80s. NSD is almost 20 years old now. PowerDNS has also been around for a long time. I don't know exactly how long, but there hasn't been any new DNS software in the last decade, I think, except for CoreDNS.
So just something kind of popped in my head there as you were talking. Like, I guess, DNS is as old as the internet, right? At least is what we think of. Is that protocol still evolving? Is it still changing, or is it relatively static?
So the core of the protocol has been static since 1984-ish. But a lot of stuff has happened. I mean, it's all plain text. It's easy to spoof. So there was this effort for DNSSEC to actually make it more secure. That made the protocol way more complex, and not everybody is actually using it. So it's questionable if that was a good idea. And because it's so old, it runs on UDP, and having to do your own networking with UDP is pretty hard. So you see new things popping up, which actually are in the presentation. The protocol called DO is DNS over HTTP, which is interesting. And QUIC is a new protocol being finalized, I think, by the IETF. So DOC is another thing that's coming along, which means we're going to do DNS over QUIC. So there's a lot of stuff happening in that area as well. And corner cases are still being found, and they need an RFC to detail them and how that actually properly works. So even though it's an old protocol, a lot of new things are happening in that space. The core protocol has been static, as I said, for decades now.
That's pretty cool. Okay. So, again, I mean, DNSSEC, you've mentioned that twice now, and it's one of those things that I know I'm supposed to enable on my domains, and then I just never actually do. So I'm sure I should. I probably will try it one day, but I'll skip it for now.
It's complex. Although I wrote a thing for that in CoreDNS because I got annoyed with it as well. And Bind is getting better, and even NSD and PowerDNS have good tooling for that as well. But no, you do it on your server and nobody validates those signatures you're adding, it doesn't add any value.
Okay. It sounds like you're kind of scratching a lot of your own itches or pain points with CoreDNS. It's like you're getting frustrated with things and you're going, right, I can do this better. Is that a fair guess or assumption?
Yeah, well, that's how it started, because I want to have Prometheus metrics from Bind, and Bind doesn't do this out of the box, so you have intermediate binary, which compiles some stuff from XML, but Bind output it at a time. So that led to me thinking, I have this Go DNS library, which is pretty okay. How hard can it be to actually write a DNS server? And at the time, I was looking at a new web server for the whole Let's Encrypt stuff, and Caddy, a Go server written by Matt Holt, did all that stuff, and that looked pretty amazing. And that got me thinking, like, maybe I can use the same model that Caddy is using and just write a DNS server. And that's actually, I forked Caddy and basically replaced HTTP with DNS in the source code after 2 weeks of building that. Compiled it, and it was resembling a DNS server. So that was pretty much my own itch to, and it did, of course, Prometheus metrics. So that was my own itch that I scratched, and that blossomed into CoreDNS. Amazing.
And that's great that you had the Caddy project there, something you could just kind of use as, I guess, the server boilerplate, and then work in all the DNS logic and stuff like that.
Yeah. The whole plugin idea is copied from Caddy.
Very cool. So I believe we're going to start today's session with a little bit of an introduction and some slides. So I'll get your...
Yep.
There we go. Your slides are now live.
Thank you. Yeah, so as we just discussed, like CoreDNS, very much an emphasis on a flexible server. The plugin idea that we briefly touched upon makes it easy to add stuff in CoreDNS. So you don't need to be a full expert to have stuff working in your server. And also discussed, DNS looks like a very simple protocol, but there's many corner cases which makes it really, really tricky to deal with. And also people expect speed, so it also needs to be blazingly fast, otherwise you get latencies in all your application. So let's talk about the plugins. Without plugins, CoreDNS basically doesn't do anything. And a plugin is similar to a web server stack middleware. The original word in CoreDNS was even middleware, which Caddy was at the time used middleware and plugins. We settled on plugins at some point. We have quite a bit, I think 30-ish, and they are all configured compile time. And we have a file called plugin.config, which tells you what plugins are available in CoreDNS. Here you see a couple of them. Metadata, that's a plugin that adds a little bit of metadata, like MAC address. You can add that if you want. Cancel is to cancel a context on the query. TLS is to set up TLS, which is useful for DNS over HTTP, for instance, or gRPC. Reload will reload the CoreDNS process if it sees changes in its config file. So there's a whole range of what plugins can do, but it's all implemented as a plugin. NSID stands for name server ID. It's a little tag you can add to a DNS request that tells you when you hit an Anycast server, which server actually responded to your request. So that could be useful for debugging. So there's a whole range of stuff that we have in CoreDNS. So one of the things that people struggle with is in which order are the plugins processed when the CoreDNS sees a query. And the order is done compile time, and the order is what the order is in plugin.config. So it doesn't matter how your config looks, the order is already predetermined by compiling this file into CoreDNS, so to say. So plugin.config specifies which plugins you have and in which order they will be executed. And the core file, which is the config file for CoreDNS, specifies the plugin usage for your specific server. It would be nice if this was all dynamic. Go doesn't do this yet. Maybe in some future rewrite, we will revisit this whole idea and it becomes more natural. For now, this is how we do things. So to look specifically, if I have a config file, a core file, with the following plugins, cache, whoami, and log, then if I get a query from the outside to CoreDNS, I need to look into the plugin.config and see where these plugins are actually configured. So cache is on line 44, whoami is on line 64, and log is on line 37. Meaning log will be seen first, then cache will see the query, and then whoami will see the query, and then you get a reply. So the ordering here in the core file doesn't matter on how this query is being processed.
So can I ask a question about that, if you're happy to take them in line? I guess that's a good thing though, right? I'm assuming that the plugin developers and yourself and the other contributors, you understand the ordering semantics that makes sense for each of these plugins, rather than leaving it into the hands of the person writing their own core file, where they could have cache at the very end and it never actually being used at all. So I guess this is a good feature, and I guess something that people just need to be aware of.
Yes and no. So we do get bug reports by people saying like my plugin is not executed, and then it's like where it is, where do you put the plugin in your plugin.config, which is like I put it last, which is like then it won't get seen probably. But sometimes you have two plugins that need to be on position 5, for instance, and then you need to make a decision which one goes first. Which if you could just revert the order in the core file, you wouldn't have that problem. So it is what it is. could be better. I quite like this because it's really deterministic. You can just see what's happening. On those plugins, we have a whole range of them. We are discussing, do we need to make this an official type of plugin? But there are so many and it's so liberal what you can do in a plugin. It's pretty hard to do this properly. But we have plugins that generate some response. Whoami forward, which goes to another server to fetch a response and return it. Kubernetes plugin, which gets its data from the Kubernetes API. Other things are queries that are inspected. A log is such a thing. It doesn't really inspect it, but it looks at the query and then parses it and logs what it sees. Cache, obviously, will cache a query, so it will see the query, put it in its cache if the response isn't there yet. You can inspect the query and change it. Rewrite, template, buff size, all do this. NSID is one of those as well. You have plugins that affect the whole process. Health, used in Kubernetes to report a health endpoint. Readiness, another thing used in Kubernetes. Reload, we saw this. On, you can do, if you reload a config file, you can execute a binary on disk. And metrics that actually exports Prometheus metrics. One of the reasons that I actually wanted CoreDNS in the first place. And for core file helpers, you can import another file or a snippet to make your core file readable. Each of these has a README. They're all published on CoreDNS.io. I made a Debian package where I package these all up as manual pages as well. So that's a good set of documentation. It mostly tells you how to use a plugin. Becomes interesting if there's interaction between different plugins and how you debug stuff, which is something we will see later in this presentation on plugins that might help you there. Okay, let's delve into a config and see how this works. So we have two config files. This one is plain DNS, and what does it say? I am authoritative for the root zone, which is basically the entirety of DNS. And I will run on this port number. And this server will have a whoami plugin and a log plugin, meaning it will respond to it and it will log this. The new protocol, DO, DNS over HTTP. Similar thing, except you just prefix the domain with https://. I'm not sure what Quick will do, but it's probably also going to be HTTPS. So I'm not sure how we're going to make that different in a core file. It needs to run on a different port in this case. So we do this one. Also the whoami plugin, the log plugin, and I need TLS configured for DO. It doesn't work if you don't have TLS. This is interesting, especially if you look at, for instance, Caddy and Let's Encrypt. It would be cool if we could automate this in a similar way, but being a DNS server has some interesting things that we need to look in. Let's see how this works. Let's shift to my terminal. So I have a couple of things here. I found a Python utility called Homer, which actually speaks DNS over HTTP, because my go-to utility, dig, doesn't do it yet. So I have a core file here, which is basically the thing I just shown you. It's one core file, so this core file will start two internal servers, one DO server and one a normal one. And there's not so much to it. I can just give CoreDNS - core file. Port numbers are already specified in the core file, so this should just start. And it does. We have this server starting for the root zone, and a DO server also for the root zone on this port. Skip to this. So dig at localhost a record, who am I? This will give me a reply. And you see who am I replied to me. I get this data back, which is a bit nonsensical. It tells who am I, which is my IP address and the port number I was asking the question on, and the protocol. It's a bit silly, but it's a nice tool for debug things and demos like this. Nice. You also see it's logged, which is what the log plugin does. So I prepared a little shell script. This goes to the other port, 1443. And it asks the same question over HTTPS. It's a bit silly. The actual ID is always 0, which is not how it should be. The buffer size, because we're asking over TCP, defaults to this value. That's all details. But you see here that we actually query CoreDNS on this URL because it's HTTPS, and we get a similar answer. You see here it's TCP because it's HTTPS, different port, but we're still coming from localhost. So this works. You can just use CoreDNS as a server that does DO. Quick will be added once that's fully specified. One thing we're not doing yet is we can't forward queries to DNS over HTTP server. We are missing a plugin that does that. Cool.
So do you see DNS over HTTPS? Is that the new standard now? Would you say always default to that if possible? I mean, are there any considerations that people should be making, like, start with the UDP approach and then bring it in, phase it in? Like, what's your thoughts on that?
So with Doe, browsers do this now natively, meaning the whole DNS ecosystem was always, you need to upgrade every box on Earth to actually have your code being deployed in the resolve on the machines. Now Google just pushes out a new version of Chrome, and everybody is using an upgraded version of DNS over HTTPS. And there's this whole thing, what I said, like DNS was plain text. DNSSEC didn't change that, it just added signatures. So with Doe, for the first time, you actually can't inspect DNS traffic, which is interesting in certain parts of the world. Or maybe all of them, but that's a whole different discussion. So that's one of the main drivers for DNS over HTTPS.
I don't want to diverge too much, but I'll ask one more question. Do the metrics the CoreDNS exposed, does that give me a breakdown of the protocol it was handled? Will it tell me if it was DNS over HTTPS or whether it was plain DNS?
No, I think we only do UDP TCP, which might be an interesting thing to add.
Okay, cool. I'll play around with that.
Yeah, can we see? Yeah, we can definitely see how it comes in. So that might actually be a nice thing to have. Running both a UDP service and HTTPS service is kind of strange because then nobody can see my queries because you're still doing the plain old UDP. But a fair point. No, scrolling the wrong window. On those multiple servers. So this is a core file that defines two servers, basically, two internal CoreDNS servers. One serves the example.org domain on port 1053, and the other one serves the example.net domain on 1053. So these are the same listener, but internally this means there are two servers in CoreDNS responding to queries for these two domains. And you can see the difference, which I will show. One of the servers will log because it has the log plugin, and the other one will stay silent and won't do anything. Note that if you enable the log plugin, if you have a busy server and you are logging a lot, that will take away some performance. Going back to my terminal. So stop this. So this is the core file from the slide. Same here, I populated all these directories with a CoreDNS binary, so to make it nice and easy. We started, it prints out all these mini servers it's running. So those are those two. And we can do the same thing as just now. I have a dig for example.net, so this shouldn't show anything on the CoreDNS side, which it didn't because it didn't have the log plugin. But if I'll ask one for org, it does give a log line because it has a plugin that says it must do so. On what you see here, it's pretty basic. This is the remote address, so the resolver asking. Can't actually remember what this was, but this is what the question was. Protocol, size of the incoming request. Do I want DNSSEC or not? And what my UDP buffer is. And then this stuff is the actual answer. So we didn't see an error. The answer was 112 bytes, and it took this amount of time to actually generate it. And some of this stuff is also in the metrics if you have metrics enabled.
Okay. So is it a standard practice for like, looking at that config, I mean, and now knowing that it came from the caddy kind of background. Those are essentially like virtual hosts, and then you're just kind of using that similar format for the DNS response. Would you run them on different ports, or would that just always be the same port?
No, you can also run them on different ports. Then you actually get multiple listeners in the CoreDNS process to pick those up. But yes.
Okay, cool.
Yeah, I can change the port, and then I need to change the ports in the dig command as well. There's no difference.
All right, just curious.
So one of the big things in DNS is that it's super hard to debug. And I will not claim that these following slides will make you a debug expert, because it's still hard. A couple of reasons why this is hard, mostly because the volume of DNS queries is probably large. So if 1 in 1,000 queries fails, how do you see this one query failing? Even though somebody actually had a problem with the application because that one query timed out or whatever. So that's a thing. And what I said, logging on scale is hard to do. So it's really hard to just find like 1 in a million queries that timed out for some reason, which is why, and because CoreDNS is low in the stack, anything that fails to properly work here has repercussions higher up, which means things don't work or have a humongous amount of latency. So a couple of plugins. We have the debug plugin. That's a fairly new thing. You can log debug from within a plugin. And if you enable the debug plugin, that actually shows up in your output, in standard output. It also stops CoreDNS recovering from panics. Panic's a go thing. If CoreDNS has an out of bounds read, it will crash. By default, it will then just restart. Or it will not actually crash, it will intercept the panic and will just continue running. Furthermore, there's pprof. So there is for Go pprofing. You can just enable a plugin, connect to the remote port, and get a pprof of the binary. Prometheus already talked about adding metrics, which you always should. And trace does actual open tracing of the requests within CoreDNS. Those are all useful things to have. Especially tracing can be handy to just see what's happening. Although it's not too interesting, because usually CoreDNS sees a query, forwards it to the upstream, and then gives back an answer, which it may or may not get. Another thing that we have is dnstap, which is a gRPC protocol which forwards all generated queries to a dnstap endpoint, and will allow you to see what queries are received by CoreDNS and what queries CoreDNS itself also does. And as with always, it's just enabling a plugin. So this stanza of core file, we run a server for the root domain, so we capture all incoming queries. We will forward them to Google. We will log the queries, but we'll also dnstap the queries to the socket. And on the other side of that socket needs to be running a dnstap binary, which will show you the queries being received and the queries being forwarded to Google. So this can be really, really powerful in actually seeing and capturing what is happening with this process. Note that a lot of stuff, especially in Kubernetes, we've seen issues where IP tables are filling up. So if the query doesn't reach CoreDNS, this will be useless. Then you will need to dnstap on your node to actually see where is the traffic going. And usually it's dropped. We've seen it quite a lot of times in Kubernetes, for instance. Okay, I prepared a demo for this as well, so I will switch to my terminal. Quit. The core file, I've added debug for good measure here, which is fine. So this is the same core file I've just shown. Let me start my dnstap binary. So this open a socket, Unix socket on temp dnstap.sock. And it will, I think, barf out YAML So we should see some YAML if I start CoreDNS.
We all love YAML.
Yeah, it's also JSON, so maybe I should have done it. Let's query this and ask for the MX records of example. .NET. We've seen a bunch of things. Of course, this is the answer that I got from CoreDNS. Don't look at how this looks, but this is a valid answer that basically says we don't have any MXs. We have a log line because we enabled that as well. And we all have our dnstap data. And this is interesting because what you didn't see in the log line is that we are also forwarding this to the server, and we are asking the same question, so that's good. The MX records for example.net, and it responded. So we got a forwarded response, and you see it here, which is right now we see the original query coming in, so it's a bit of ordering. It makes sense if you know what's happened, but this is the query coming into CoreDNS, which is indeed asking for this. And this is the actual response that we sent back, which is the forwarded message we received. So these are 4 data points, 2 queries sent and 2 queries received, which you don't get from the logs, and you also don't see from the dig, obviously, because that's just the client. Nice. Note that the protocol itself is not UDP based, it's gRPC based. So it is not as efficient. So it might block or it might build up if you have a large number of queries hitting CoreDNS. Although I don't know what the specific number would be, but it's especially you can also do dnstap over TCP, so there might be some slowness there. By default, if we can't dnstap a message, we will drop it because we can't wait for dnstap to be ready for us. But this is a very useful debugging tool that I don't think a lot of people know about.
Yeah, I mean, there's this meme, right? Every time something goes wrong, it's always DNS. And I think the visibility here that I can see dnstap giving people would probably help them debug those things so much quicker than the long drawn out way that I can say from experience I've spent looking at DNS problems. So I wish I had known this existed a long time ago.
Yeah, but you have to have the bandwidth to actually get all this data. You have to store it maybe for a couple of days. In this format, it's pretty voluminous, so it might be a lot of data that you need to catch. But yes, it's totally doable with.
But it has that output formatter, right? You chose YAML, but I could have chose JSON. So I'm assuming I could, hook in a little bit of tooling to pull out the fields I need and store them in, a TSDB or some other DB, and then.
Yeah.
Delete them after 72 hours, but they're there when I have a problem and I want to fix it. So
yeah, exactly. And you can actually look back. Timestamps are there, so it's we can't do this in our logging, for instance, because that just wouldn't scale. So this is a good in between.
Oh, yeah, definitely. See the forwarding. So right now, this core file is saying does that say forward? The dot means anything, and then if we can't answer it, go to A to A. If I have another domain in there, can you help me understand how that works? So let me phrase that question in a way that makes sense to you. If I add another domain, like example.net, to this core file, and it doesn't have a forward, that dot is a wildcard. Is my understanding?
Yeah. So basically, what you can do, let's say you have this. And you can say, so now you are authoritative for example.org, but anything on the org you want to forward. The rest you want to handle locally in this CoreDNS binary.
Okay. And maybe this is something that you're going to cover later, and I'm just jumping the gun a little bit. How about, can I also have any number of entries for if I want each subdomain of my domain to be its own resolver, is that possible too, just by adding extra subdomains? Does that make sense?
Yeah, so you want what do you mean? Like resolve?
If I wanted david.example.org to have its own name server, that's just a case of doing that, right? Or
Yes, although doing this locally in the core file just makes CoreDNS know about it. If you want to do the proper delegation, you need somebody else actually pointing your, you need to buy the domain and go through all those things. But yes, once you've done that, you can just add the name here.
Okay, I'm just going to keep these questions coming until you tell me to shut up now. But it's the forward use the same protocol that I query. So if I query over DNS over HTTPS, does it forward in the same protocol, or does it forward over UDP by default?
By default, this is UDP. There are options, I think, force TCP, which will force a TCP connection to the upstream. The one thing that we did implement, because it was fairly easy, is I believe this syntax, which should actually work nowadays, means use DNS over TCP. No, use DNS over TLS, which is a different protocol than DNS over HTTPS. Basically, this is a raw TCP connection, and you do a TLS handshake on it. So this is supported. We have a gRPC plugin, which is similar to forward, but uses gRPC in a protobuf we invented to talk to an upstream. What we don't have is an HTTPS forwarder that actually talks DO to an upstream. That doesn't exist.
Okay.
So we can do DO on the entrance side into CoreDNS, but we can't speak it to an upstream yet.
Okay, cool.
Okay, let me switch back then. What I said. If this doesn't give you the data you want, you definitely need the TCP dumps. That's also useful for bug reporting on the CoreDNS repo. If you have a really strange case, I will probably ask TCP dump or I can't debug. Now a slight detour on from operational to some Go code. I will show you an actual plugin, which is fairly simple. As said, we are using the Go language, so a plugin is a thing that implements the plugin-plugin interface, which means in our case that you need to implement the serve DNS, which is the meat of the plugin, and a name method. And we have an example plugin, which is on CoreDNS/example repo, which prints the word example on every query it sees, so it doesn't do a lot. But the code is basically here. We have our structure that we defined, example in this case. We have a serve DNS method, gets a context, a DNS response writer. If you've ever programmed with a net HTTP package, this looks similar, except it's DNS instead of HTTP. And the request, the incoming request. The thing does something, it returns a status code and an error. And in this case, we make a new response writer, which we will see in the next slide. And we call into our plugin chain to further handle the request. Or if nothing is to be done, we are done and we will return an answer. So the new response printer thing, that is here. And the meat of this is this bit. Once we are done, we will call write message, which will write the message back to the client asking for a response. We have a response, which is either forwarded or whatever. We don't know at this point. We have just a response that we need to write back. So this is printing out example, which is what this plugin does. And then it just writes, calls the underlying response writer, calls its write message method, and will write the method, will write the response back to the client. And these can be wrapped, so this can be calling into caching, which you can call into logging, and it just unwraps the whole thing until the client actually sees the bytes being returned. And that's it. And in this case, you don't need to know anything about DNS. You just write a couple of lines of Go, and you have a plugin. It's not always that easy.
That's pretty simple, actually. To be honest, I figured the plugins would have a little bit. I guess there's more to it than that, but the base skeleton actually is not that daunting at all.
Yeah, and we're trying actively to make like the core of CoreDNS to do most of the DNS stuff. So you can actually focus on just writing Go code, and you just hook it in, and it works. Sadly, there are many corner cases in the DNS which you need to think about. But yeah, in essence, we want to make open up DNS for people to just use this. So one of the things we're seeing is that the crypto people, there's like some naming scheme they have on the some Bitcoin coin, and they wrote a plugin in CoreDNS that works on the blockchain and does some naming.
Yeah, I was going through the plugin list earlier, and I noticed the Ethereum DNS server plugin was just kind of sitting there, and I found that quite interesting. That it's not just the Kubernetes community and the cloud native community, but the broader technology community is now coming to CoreDNS and adding their own plugins to it, which I thought was really cool.
Yeah, I think so too. I have no idea what the thing actually does, but it's just nice that people can prototype and just make that thing easily work in CoreDNS. Much harder than doing it in bind, for instance, or NSD. I don't know about PowerDNS. So that's it. We of course use CoreDNS ourselves to host CoreDNS.io, which is one of the things we want to move to Netherfly, but they don't do IPv6, and hosting our own DNS there is more interesting. So for now, we just host this on a Linux machine. And the core file that we have for CoreDNS.io looks like this. So we have a snippet, as it's called, because I'm using this to serve more domains. So this just defines that we have Prometheus, errors, debug, and any. Any is another small plugin that replies to any queries with the hinfo. Any replies can be really, really big, so they are used for amplification attacks. With any plugin, you just sidestep the whole problem. And then for CoreDNS.io is a domain we serve, so we spell it out in the core file. And we have a couple of things here. We use the sign plugin to DNSSEC sign CoreDNS.io. Because I've done DNSSEC, I thought it should be signed with, should be using DNSSEC. We have some keys on the system that just signs this stuff. Then we use the file plugin to pick up this sign zone, which is created by the sign plugin, and serve the contents. Then we have the transfer plugin that tells you if this zone is changed, ping those other servers, because we need them to pick up the new content that we have. And then we import base, which means we also have the plugins that we have on the left side here. These things make DNSSEC sign zones hassle-free. It will just re-sign and will do the right thing. And you can see this from the logging. So the logs from CoreDNS, I grabbed this like a couple of days ago. The sign plugin is telling me that it's just re-signed CoreDNS.io because the signatures are too old. And they have a lifetime. It goes a bit deep in what DNSSEC is, but they have a lifetime, so you have to re-sign those things every so often. Otherwise, your zone will go bad. So thankfully, this worked. It will say some more bits, like when I'm going to sign again. It's super small zone, so the signing took no time at all. But then you see that the file plugin sees that the CoreDNS.io zone has been re-signed or changed in that file, and it picks up the new file and serves the new data. When file that does this, it will then ping the transfer plugin, which will send notifies, as they are called, to the other servers, like, look guys, I have a new zone, you need to pick it up and you need to get the new data from me. So here you see all the plugins, like in the actual plugin chain, just ticking those boxes one by one and just have the whole thing automated without me doing anything. which is why I wanted to sign plugin, because before this I had a cron job, which was a bit crummy.
So I'm curious about that transfer plugin where it's notifying another IP address. Like, is CoreDNS horizontally scalable? Is that, am I misunderstanding?
This is that's an old feature of DNS servers. But yeah, the proper term now would be horizontally scalable, yes.
So is that just two core files that are the same being run by the binary but on different machines? Is that all I do?
Yeah. Well, preferably you want to run that somebody else runs a different binary in a different org. So these are a couple of old friends of mine who actually run a different DNS server, but it serves the same data.
Okay, cool.
I'm contemplating making a thing that uses BitTorrent to do this, but it turned out to be somewhat complex. But that's all. I mean, as long as we control both ends, so both ends run CoreDNS, we are super free in what we can do. But this, the notifies and the transfer is the standard DNS protocol.
Right. Okay. Cool.
Which is a different protocol than the normal query and answer protocol. Cool. This is my last slide. So what are we going to do in CoreDNS? Well, the usual bug fixing and keeping up to date with Kubernetes, which is moving fast, adding dual stack support, which is super nice, and some other API stuff that's been done there. Furthermore, a couple of new plugins that are core to DNS. There is one to minimize responses, which is saves bandwidth and amplification attacks. DNS cookies is a thing to actually make sure you're talking to the right server, which you might implement as a plugin. One thing that I've been pushing back is new storage plugins, because they are quite complex and they vendor the entire world. So I think we have a lot of stuff that we need to pull down to compile CoreDNS, mostly because of we're using etcd, Cloud DNS, Route 53, Azure, a whole bunch of these, and all those plugins look similar. So we need some kind of generic plugin where you can hook in all these to make that scale again, I think. So for now, I've had enough of adding identical code to go to a slightly backend. So I'm putting my foot down unless there's a good reason to actually include something super new and novel.
Okay.
So that's it from my side.
All right. So if anyone watching has any questions, feel free to drop them in the comment section now. I have a few that I prepared that I'll run over just now then. And I think my first question actually very luckily ended on a similar note to what you were talking about there. Like when I was looking at the website earlier and I realized there's plugins and external plugins, it kind of reminded me of a problem we had on the Telegraph project. The Telegraph project is a collection agent for metrics. But they started off as a plugin-based thing, but all the plugins were compiled in. Now, the Telegraph project today has like over 220 plugins. The project is size, the binary is huge. The vendor, wow, the vendors like, and I think that's a very Go problem, right? Like Go problem. There's not a good plugin mechanism that works with Go. And I'm curious about the external plugins and how that works in CoreDNS. Is it gRPC, HTTP, something else? Maybe you could help me understand that a little bit.
So what is your exact question? Like, how do you get them in, or how do we deal with how do you move from external to internal?
So are the external plugins just not hosted in the CoreDNS repository, but still compiled in, or are you doing some magic at runtime to pull in external plugins?
No. So if you want to have an external plugin, you need to exchange plugin.config to actually add the lines to point to the external plugin, then a Go generate, and then a Go build.
Okay, so that's still an outstanding problem then for Go projects is how do we have external plugins that can be dynamically linked or something like that?
Yeah, there's this plugin interface, but I haven't looked into that. So if we're going to go that route, that would be a massive rewrite, which means we can also look in the plugin ordering because we lose the plugin.config file probably. But yeah, I'm happy enough with CoreDNS as is that I don't consider this personally a big thing that I need to fix in CoreDNS.
Okay, cool. So I'm curious also about, we touched on I kind of misinterpreted the transfer plugin for something to do with scaling a DNS server, but I'm also curious about the bad actor side of that. Like DNS attacking DNS servers can be a popular vector, I guess, for people that want to bring down or take over DNS zones and stuff like that. Does CoreDNS have plugins or anything that allows me to do to try and protect myself?
There is an external plugin called response rate limiting, which means that if we see a lot of queries from the same IP, we will do some blocking. That's not a default plugin. Usually, there's several ways. Like if you want to interact with the registration and that kind of stuff, that's not something CoreDNS itself can help with. I mean, it just serves whatever is in the core file. So if somebody gets into that trajectory, then so be it. The transfer itself, there is some very limited things you can do to securities, which also shows the age of DNS protocol. There's a symmetric key you can configure, IP whitelisting, that kind of stuff, which is all, in my book, pretty old school things to actually make sure you receive the correct data. The best way to make a DNS server not responsive is just DDoS it and fill the pipe. And there's not much you can do at that point.
Okay. I'm assuming your personal domains are all hosted by CoreDNS. Is that a correct assumption?
Yeah. Yeah, the snippet that I showed you on the CoreDNS show, that has my other domains there as well.
Of course. All right, I'll give you two proper questions now instead of that. So, obviously, I think a lot of people are familiar with CoreDNS because of the adoption of Kubernetes and CoreDNS into that project. Like with the whole advent of cloud-native architectures and microservices becoming a new norm for teams and organizations, does that allow or afford DNS to play a newer role in those architectures or take on new responsibilities?
So yeah, there was a massive influx of popularity once we got into the CNCF. Also a humongous amount of bugs that we fixed because people were now actually using it. So one of the things we try to do with gRPC is we can probably move away from UDP if everything is CoreDNS, which means we can use new protocols and can do interesting things. One of the things we had with gRPC was that you could watch names to be changed. In the DNS right now, you have to wait until the TTL expires and that kind of stuff. But the gRPC, we could just get a watch back, like this name has changed, you need to update it, which would mean that the updates in Kubernetes, for instance, would be instantaneously instead of just waiting for a TTL to time out. So that would be interesting, but then this all falls flat because you also need to change the clients to actually use your newfangled protocol. Meaning at the time, local DNS node local, what is it? Node DNS local, whatever the hell they have right now. Every node in the in the Kubernetes cluster runs CoreDNS. So we can now potentially actually do this. We could probably switch to gRPC and have some other protocol than DNS doing the naming in those clusters.
All right, cool. That actually kind of leads on. We had a viewer question, and the question was, is there any best practices for using DNS in Kubernetes? And I'd also like to kind of just throw something else into there. Like you mentioned that you previously worked on SkyDNS, which I think was the original kubeDNS. Like why was that deprecated in favor of CoreDNS? Like what were some of the differences, changes? What lessons did we learn from that kind of older approach?
So to start with that, so SkyDNS was the SkyDNS binary combined with DNS mask, which was another C DNS binary. And there was at some moment, a couple of years back, where they had 8 CFEs in DNS mask. So that was a thing they needed to upgrade. Also, the interaction between the two, because you have 2 binaries, became more complex. So CoreDNS basically unified that all, gave proper metrics, all that kind of stuff. So it's easier to deploy one CoreDNS than it is to have SkyDNS and DNS mask. So that was a bit of the impetus on why moving to CoreDNS. Doing DNS in Kubernetes clusters is tricky for a couple of reasons. There's a thing called the search path, and some options you can have, which means if you have a domain like www.google.com, the entire search path will be searched before it will actually try www.google.com. Meaning every query that is done in a Kubernetes cluster leads to a 5x amplification of the number of queries we see in CoreDNS. So that alone is horrendous and should be fixed, although it can't be fixed anymore. So the number of queries that we see is way more than need to be done, which means you need to scale CoreDNS aggressively, or your DNS in clusters aggressively, to actually be able to respond to all those queries. We have a couple of attacks that sidestep this. There is AutoPath, which makes it shortcuts your search path because we know what you're looking for, so we will tell you what the actual answer is. But that's quite a hack. So if you want to know if things are performing well, use metrics. The health plugin has an internal loop that tells you how busy the CoreDNS binary is. So you can use that for latency. If that goes through the roof, then something is clearly wrong. Latency on DNS requests is also good to track. Sysdig had an article yesterday on exactly that. So you need to be on top of things to see what's happening. And if you look at the metrics, you see that non-existing domains is 90% of all queries.
Yeah, the minute you said that search path thing, like I got instant flashbacks. Like when kubeDNS was the default in our clusters, we pretty much did denial of service attack our entire infrastructure with them and a request that we're going through it. And the configuration is that it was the ndots problem, right? I think by default ndots is set to like 5 or something like that, and it was causing 5x number of lookups than we actually wanted. And when you have a high number of lookups, the whole thing was falling down.
The default on your Linux box is 2 for ndots to give a sense of how far along they went. Another thing that you should probably do in your Kubernetes cluster is normally you have 2 DNS servers that are useful for clients. In Kubernetes clusters, there's one service IP and all clients go to this. So if that's overloaded, a client will just redo the query. So once you have a cascading failure, there's no way we can come out of this. So what you should have is 2 sets of CoreDNS serving 2 different service IPs, and then updating all your nodes to have those 2 IPs in the resolve.conf. And then at least a client can move to the other one, which is maybe less loaded than the previous one.
Yeah, that's a great tip, actually. That's nice.
I wish I was involved in these decisions when they were made in Kubernetes, but you know.
There's still time. You can fail a cat. We can get that changed. We can make it better. I mean, I think it's definitely
and the search path that will never change.
All right. I don't think we have any more questions. So with that, I'll just say, thank you for joining me today. It was really insightful, getting your experience and your understanding of the project and the demos, and just getting a good look into how CoreDNS functions and how the plugins work. Like, all of that was great. So thank you for taking the time to join me today.
Cool. Thanks for having me.
All right. Well, you have a great evening. I know it's getting late where you are, so I won't keep you much longer. But again, a pleasure, and I'll speak to you soon.
Cool. Great. Thanks. Bye-bye.